Students, as we discussed the what? The problems, that is theoretical part regarding the centroid, as we discussed already, GA bar plus GB bar plus GC bar is equal to 0 bar, and AC bar plus GB bar plus GC bar is equal to 2 into AC bar. Like that, we come across many results. And one of the last result in the centroid is let AB bar is equal to B bar, AC bar is equal to C bar, AB bar is equal to B bar, AC bar is equal to C bar. Then AC bar is equal to dash. It is also a result of a what? Centroid. Now what I do is, let us add these two. Now AB bar plus AC bar is equal to B bar plus C bar. This vector can be expressed as OB minus OA, OC minus OA is equal to B bar plus C bar. So therefore, OB plus OC minus 2OA is equal to B bar plus C bar. Add and subtract OA bar, OB bar, OC bar, 3 into OA bar plus B bar plus C bar. As we have added already OA, that is subtract OA, with minus 2 OA, another OA, it's a 3 OA. So this can be written as 3 into OC bar minus 3 into OA bar is equal to B bar plus C bar, since 3 into OC bar is equal to OA bar plus OB bar plus OC bar. So therefore, take out the 3 outside. Thus becomes OC minus OA is equal to B bar plus C bar. Thus becomes 3 into AC bar is equal to B bar plus C bar, which implies AC bar is equal to B bar plus C bar by 3. Similarly, you can also go for in the cyclic order, different sides you can take it. So therefore, as you know already, let AB bar is equal to B bar, AC bar is equal to C bar, then AC bar is equal to dash. So now what I did, just I added the two vectors. I got it, AB bar plus AC bar is equal to B bar plus C bar. Next, every vector can be expressed as position vectors of its extremities. That is OB minus OA, OC minus OA, B bar plus C bar. So therefore, OB bar plus OC bar minus 2 into OA bar is equal to B bar plus C bar. Now I want one OA bar. Why? To write this result, 3 into OC bar, I must need OA bar. From the less number to get more number of terms, either add and subtract or divide and multiply. So therefore, add and subtract OA bar plus OB bar plus OC bar minus 3 OA bar is equal to B bar plus C bar. So therefore, I can write this whole 3 terms as 3 into OC bar minus 3 into OA bar is equal to B bar plus C bar. So therefore, 3 into OC minus OA, B bar plus C bar. Therefore, it's about AC bar, the position vector of a terminal point minus position vector of initial point, 3 into AC bar. Later, AC bar is equal to B bar plus C bar by 3. As you know already, centroid is the point of concurrence of medians of a triangle. Yes, that's what I wanted to prove now. In a triangle ABC, in a triangle ABC, D, E, F are the midpoints of the sides BC bar, CA bar and AB bar respectively. Then AD bar plus BE bar plus CF bar is equal to 0 bar, is equal to 0 bar. So therefore, is equal to 0 bar or 0. We have to prove that. Now if I select this is a triangle, this is A, this is a B, it's a C, it's a D, it's a E, it's a F. AD is a median. This is also, this is. So therefore, now what I can write is D is a midpoint of BC, E is a midpoint of CA, F is a midpoint of AB respectively. What I do is, now the proof of this one is D is a midpoint of BC bar, which implies OD bar is equal to OB bar plus OC bar by 2. 2 into OD bar is equal to OB bar plus OC bar. If you want, you can take it. Now I can write similarly OE bar, E is the midpoint of this. OE bar is equal to OC bar plus OA bar by 2. 2 into OE bar is equal to OC bar plus OA bar. OF bar is equal to OA bar plus OB bar by 2, which implies 2 into OF bar is equal to OA bar plus OB bar. Now what I do is, I want AD bar. This AD bar, already we know that the position vector of D. In two ways you can prove that. What is that AD bar? I can also write here AD bar, the second method. AD bar in this triangle, in the triangle ABD, in the triangle ADC. Right? By using this also I can write. The geometrically I can also write by vector addition. I can also prove that. So therefore, the first method is for AD bar. First method AD bar is from this triangle by vector addition, AD bar is equal to AB bar plus BD bar. Similarly, in the same fashion, from this triangle, by using vector addition, I can write AD bar is equal to AC bar plus CD bar. Since D is the midpoint of BC, BD in this direction, CD in this direction, equal and opposite in direction. Both BD and CD get cancels. Add up. This gives 2 times of AD bar is equal to AB bar plus AC bar. Remember, hereafter it's a resolution of a vector. This AD bar can be written as sum of these two vectors from where it is starting from A. Therefore, AD bar can be written as AB bar plus AC bar by 2. That's what we did. Similarly, I can also write 2 times of BE bar. From here you are starting. BC bar plus BA bar by 2. How, sir? By using the same proof only. Therefore, BC bar plus BA bar. Right? Now, I can also write CF bar, 2 into CF bar. From C it starts, CB bar plus CA bar, CB bar plus CA bar. Yes, now you call this as 1, you call this as 2, you call this as 3. Add up 1 plus 2 plus 3 implies. So therefore, I can write 2 into AD bar plus BE bar plus CF bar plus CF bar is equal to, you can very well observe, here AB bar is there, addition of these two, AB bar, here BA bar, change the direction. Next AC bar, CA bar, change the direction. BC bar and CB bar, change the direction. So therefore, equal and opposite direction, all vectors get cancelled. You get what? 0 or a 0 bar, addition of these vectors. Therefore, we could prove AD bar plus BE bar, CF bar is equal to what? 0. Yes, the vector addition of the medians of a triangle is always a null vector. What is that? The vector addition of a medians of a triangle is a null vector. This is one method. Okay, we oftenly use this method while doing the medians problems. So therefore, what we proved is the vector addition of a medians of a triangle is equal to null vector. Now, as I told, the second method, this is first method. The second method is consider this AD bar, BE bar, CF bar. Every vector can be expressed as position vectors of its extremities. Right. OD bar, OE bar, OF bar. Already we wrote it. What is OD bar? OB bar plus OC bar by 2 minus OA. Next, OE bar. That is, OE bar is OC bar minus OA bar by 2 minus OB bar. What is OF bar? OA bar plus OB bar by 2 minus OC bar, right? So therefore, I can write this one as take LCM, OB bar plus OC bar minus 2 OA bar, OC bar minus OA bar minus 2 times of OB bar, OA bar, this is plus, this is OC, this is plus. Next, OA bar plus OB bar minus 2 times of OC bar whole divided by 2. Now, OB plus OC minus 2 OA, OC plus OA minus 2 OB, OA plus OB minus 2 OC. So therefore, now look here, yes, now OA bar, this 2 OA bar, this 2 OA bar get cancels. OB bar minus 2 into OB bar, OC bar minus 2 into OC bar, all terms get cancels. 0 by 2 is equal to 0. Thus, we have proved the vector addition of a medians of a triangle is always equal to null vector or a what? 0. Yes, null vector or a 0. And also this is second method. We have went for the second method is every vector can be expressed as position vectors of its extremities. Whereas in the first method, we went every vector, when it is about AD bar, it can be resoluted as AD bar is equal to AB bar plus AC bar by 2. B bar is equal to BA bar plus BC bar by 2. Next, CF bar can be written as CB bar plus CA bar by 2. Okay, both are having its own advantage, more weightage, right? So therefore, now we came to know that the vector addition of a medians of a triangle is equal to 0. The next important one is very, very important from the objective in terms. Now if I go to this one is, take this is OA bar. OA bar is equal to A bar. OB bar is equal to B bar. This is the OL is the bisector of OA and OB. OL is a what? Bisector of A bar and B bar. So therefore, let us consider a point P on the bisector. So therefore, now if I join these two, when this is a bisector, on the bisector I took P. Therefore, P acts as, I can write, now you take this as what? A dash. You take this as a B dash. So therefore, now I will write, note, the vector along the bisector of A bar and B bar. The vector along the bisector of A bar and B bar. When you know the vector, we can also find out the unit vector along the bisector of A bar and B bar. The vector along what? The bisector of A bar and B bar. The proof of this one is, let OA bar is equal to A bar, OB bar is equal to B bar. OL is the bisector of OA bar and OB bar, or OL is the bisector of A bar and B bar. Let P be a point on OL. It's a bisector. So therefore, as I told earlier, when the point is on the bisector, you can very well observe this acts as a what? Median. I wrote, yes, AD bar is equal to sum of the two vectors by 2. So therefore, now by definition, I can write, yes, come on, OP bar is equal to OA dash bar plus OB dash bar. Now I want to select the unit vector in the direction of A bar is A cap. The unit vector in the direction of B bar is a B cap. So therefore, I can write OP bar is equal to A cap plus B cap. This is the vector. So what is OP bar? OP bar is parallel to the bisector OP, that is OL bar. So why it is parallel to? In vector algebra, you might have observed for collinearity and parallel vectors, the condition is same. What is that? One vector can be expressed as scalar multiple of another vector. Now, the thing is, I told parallel. Is it parallel to OP bar? No, it is collinear with what? OP bar. It's a collinear with what? OP bar. So therefore, is it collinear with OP bar? It's a parallel with what? OP bar, OL bar, correct or not? So therefore, now this is the vector a parallel to what? OP bar. I can also write this is same as, I can also write OP bar is equal to some T into A cap plus B cap, where T belongs to R. When T is equal to 1, we are getting OP bar is equal to what? A cap plus B cap. Yes, today what we come across, the vector along the bisector of what? A bar and B bar is given to be T into A cap plus B cap. Is it parallel? It may be collinear with what? Come on, OL bar. It's a OP bar is parallel to the bisector OL bar. It may be parallel with OL bar. It may be collinear with what? Tell me, OL bar. So therefore, now OP bar is equal to A cap plus B cap, or else OP bar is equal to T into A cap plus B cap. When you know the vector, it is easy to find out a unit vector. What is unit vector? It's a direction by its magnitude. So therefore, now I will write the unit vector along bisector of A bar and B bar. Bisector, is it internal or external? It is quite obvious. It's an internal bisector of what? A bar and B bar. So therefore, the unit vector along the bisector of A bar and B bar is I can write so A cap is A cap plus B cap by modulus of A cap plus B cap is called the unit vector along the internal bisector of what? A bar and B bar. If you want, you can put T. So therefore, is it the unit vector along OP bar? Maybe along OP bar, maybe parallel to what? OP bar. Maybe what? Collinear with OP bar, maybe parallel to what? OP bar. So therefore, hereafter, the vector along the what? Bisector of A bar and B bar is A cap plus B cap. This is the unit vector along what? The OP bar, bisector of what? A bar and B bar. Okay, so therefore, now we come across about internal bisector. This is a vector along internal bisector. What is along external bisector? Let us see. Now, right? So therefore, now if I take in the what? Negative direction, if I go in the negative direction, right? So therefore, if I go in a negative direction, this is, yes, minus B cap, right? This is what? Minus A cap, right? I want to find out the bisector along the what? A cap and minus B cap. This may be the external bisector. Along this, I can write this as T into A cap minus B cap. This is the vector along the external bisector of what? A bar and B bar. That is note 2. That is what? Third point is the vector along external bisector of A bar and B bar is equal to T into A cap minus B cap. Then what is the unit vector? The fourth point is the unit vector along external bisector of A bar and B bar is equal to A cap minus B cap by modulus of A cap minus B cap. So this is the unit vector along the what? External bisector of A bar and B bar. This is the vector along the external bisector of A bar and B bar. Yes, after knowing the what? The vector along the internal bisector of A bar and B bar as T into A cap plus B cap, and the unit vector along the what? Internal bisector of A bar and B bar is what? A cap plus B cap by modulus of A cap plus B cap. And similarly, the vector along the external bisector of A bar and B bar is, it is T into A cap minus B cap. This vector by using what? Addition of vectors, you can join these two. So therefore, with the combination of this A cap and minus B cap, I can write T into A cap minus B cap. Similarly, the unit vector along the external bisector of A bar and B bar is what? A cap plus B cap by modulus of what? A cap plus B cap. Right. The fifth one is very, very, very important. Fifth point is the vector of length lambda, which is directed along the first one is internal bisector of A bar and B bar is, I can write A cap plus B cap by modulus of A cap plus B cap into lambda. Scalar multiplication of a vector is once again a vector. Similarly, the second one is along external is A cap minus B cap by into lambda. Let us see how. Now I will write this one as, this is the vector. I can write this is A bar, I can write B bar. Yes, now this is O. Now look here, if you go in a negative direction, this is, you take A dash, you take B dash, the unit vector in the direction of B bar is what? B cap. In the direction of A bar is what? A cap. Now this is, if I go in a negative direction, it is a what? Minus B cap. It's a what? Minus A cap. This is the what? Vector along the internal bisector. So therefore, if I find out this, this is the vector along the bisector of what? Internal bisector of A bar and B bar. Now you take this P, SP. So therefore, what is the vector along the internal bisector of A cap, A bar and B bar? A cap plus B cap. I mean T into A cap plus B cap. I want a unit vector. What I do is, you know it already, the proof of this one is the unit vector along the internal bisector of A bar and B bar is equal to A cap plus B cap by modulus of A cap plus, as we proved earlier. Up to here it's a unit vector, but its length is 1. I want a vector of length lambda. So therefore, now look here, if I take this is what? A bar. If this length is what? Come on, 1 unit. I want a vector of length 2 units. This length has to be multiplied with what? 2 times. As you know already, scalar multiplication of a vector. A bar is a vector, lambda is a what? Non-zero scalar. Lambda A bar is a scalar multiplication of a vector. So therefore, it's once again a vector. It will have a same direction or opposite direction, depends upon the value of lambda. So therefore, now when you go for what? 2a bar, its magnitude has been increased how many times? 2 times. 3a bar, 3 times it has been increased. Lambda times its magnitude has been increased how many times? 2 times. So therefore, now I want a vector of length lambda. This is nothing but lambda into a cap plus b cap by modulus of a cap plus b cap. So therefore, now I will write the vector of length, the vector of length lambda, which is directed along the internal bisector of a bar and b bar is equal to lambda into a cap plus b cap by modulus of a cap plus b cap. Now this is up to here, its length is 1 unit. For lambda, you have to multiply with what? Lambda into what? Unit vector. If you take its magnitude, once again its length will be what? Lambda. Its length will be lambda. So therefore, now along the external bisector, we can go for what? Lambda into a cap minus b cap by modulus of a cap minus b cap. Students, today we come across a very important result. What it is the very first one I told is the vector along the internal bisector of a bar and b bar is a t into a cap plus b cap, that is along internal bisector. Along external bisector, as I told, t into a cap minus b cap, a cap minus b cap. Next, we went for the unit vector along the internal bisector of a bar and b bar is t into or else a cap plus b cap by modulus of a cap plus b cap. Next, the unit vector along the external bisector of a bar and b bar is a cap minus b cap by modulus of a cap minus b cap. Next, we went to what discussed. So we went to discuss the vector of length lambda, which is directed along the bisector of what? A bar and B bar. So therefore, we know up to here OP bar as what? A cap plus B cap by modulus of A cap plus B cap. We want a vector of length lambda, which is directed along the bisector of A bar and B bar. You multiply lambda with what? Unit vector. You get a vector of length lambda, that is denoted with what? Lambda into A cap plus B cap by modulus of A cap plus B cap. If it is internal, if it is along internal, if it is along external, lambda into what? A cap minus B cap by modulus of A cap minus B cap. A cap minus B cap. Coming to inner triangle, internal bisectors of the sides of a triangle are concurrent, and the point of concurrence is an incenter. Now, in a triangle ABC, this is AD is the internal bisector, BE internal bisector, CF is internal bisector. Now, this OA bar is equal to, where is O? You take this a free vector, OA bar, OB bar, OC bar, right? This is called incenter. Let the length of the sides is small a, length of the side is what? Small b, length of the side is what? Small c. So therefore, what I can write is, yes, in a triangle ABC, I can take this as a note. In a triangle ABC, the internal angular bisectors are concurrent. Okay, and the point of concurrency is nothing but what? In center. The proof of this one is very simple. Look here. Let OA bar is equal to X bar, OB bar is equal to Y bar, OC bar is equal to Z bar, comma, BC, okay, BC or modulus of BC or BC is equal to A. Next, I can write that is the modulus of CA bar or CA is equal to B. Next, that is modulus of AB bar is equal to AB is equal to C. Be the lengths of the sides. So now you know it already by using the what command. When it is internal angular bisector, this is B is to C. So now I can write, if it is a bisector, internal bisector, this is A, it's a B, it's a C. If I take A, if I take B, if I take C, D, this divides in the what ratio? AB by AC is equal to BD by what? DC. But AB is what? C. AC is what? B is equal to BD by DC, which implies if I take this as B, if I take D, if I take C, which divides in the what ratio? C is to B. What ratio? C is to B. So therefore, this divides in the what ratio? C is to B. C is to B. So therefore, now what I write is, now D divides. We know that already from this concept, D divides BC in the ratio C is to B. Therefore, D is equal to, this is M n, mx2 plus nx1 divided by m plus n. I can write, yes, come on, B into OB bar, C into OC bar by B plus C. It is same as B into, that is Y bar, next C into Z bar by what? B plus C. Now, we know it already by using the what definition of what? Sides, ratio of the sides. This I divides, what I divides? In the lower classes already we come across it. This I divides A and D in the ratio. This I divides sum of these two sides, B plus C is to A. This becomes B plus C is to A. Then I divides BE in the what ratio? A plus C is to B. This I divides CF in the what ratio? A plus B is to what? C, right? A plus B is to C. So therefore, now what I can write is, that is I divides AD in the ratio B plus C is to A. So therefore, now OI bar is equal to, yes, B plus C into OD bar. Where is O? Wherever you want to take origin. OA, OB, OC, OI, OD, OE, OF. You can take, it's a free vector. Wherever you want the what, take the what? Origin. So therefore, OI is equal to B plus C into D, A into what? A. So therefore, I can write A into OA bar by B plus C plus A. So therefore, I can write OI bar is equal to B plus C into what is OD bar? OD bar is equal to, I have proved already, this becomes BY bar CZ bar by B plus C by A plus B plus C. A plus B plus C. Next, plus, yes, come on, A into X bar, correct? A into X bar. So therefore, this B plus C get cancels. I got a position vector of a in center. What is that? Come on, A into X bar, A into X bar, B into Y bar, C into Z bar, C into Z bar, wholed by A plus B plus C. Similarly, you can also find out for what? BE. You can also find it for CF by using the ratio. For BE, I divides in the ratio A plus C is to B. For what? Come on, CF, I divides in the ratio A plus B is to C. By using all this ratio of the sides, if you make use of this one, you get OI. It's a position vector of a in center, the position vector of a in center for all the three internal angular bisector. Even for AD also you'll get same, for B also you get same, for CF also you get same. So when you get same means all are meeting at a same point, means all are concurrent at a same point. So what we have to show that? Internal angular bisector of a what? Triangle or what? Concurrent. Yes, for one I have shown. In the similar fashion you can also find out for BE and CF. Hence the point of concurrence of three lines, that is AD, BE and CF, will be same. What will be same? AX bar plus BY bar plus CZ bar by what? A plus B plus C. This is nothing but a position vector of a what? In center. Hereafter, when A comma B comma C are the lengths of the sides of a triangle and whose vertices are having the position vectors X bar, Y bar, Z bar, then position vector of a in center can be written as OI bar is equal to AX bar plus BY bar plus CZ bar by what? A plus B plus C. Now look here. Now I am making a one important result. What is that? Come on. Instead of, yes, come on, X bar, I am going for what? OI bar. Yes, OI bar is equal to A into, what is X bar? OA bar. What is B into OB bar? C into OC bar by A plus B plus C. You cross multiply. If you cross multiply, OI into A, OI into B, OI into C, A into OA bar, B into B bar, OC into C bar. Therefore, OI bar into A plus B plus C is equal to A into OA bar, B into OB bar, C into OC bar. Take common factor. This becomes A into OI minus OA bar plus B into, yes, come on, OI minus OB bar. Next, C into OI bar minus OC bar is equal to 0 bar or 0, as you please. It's a 0 bar or 0. So therefore, now I can write as, that is A into AI bar. Okay, AI bar, that is B into BI bar, C into CI bar, or else I can also write A into IA bar plus B into IB bar, C into IC bar is equal to 0 bar or 0. Remember, we have arrived at a new result with the concept of, with the definition of what? In center. What's the command? That is A into IA bar plus B into IB bar plus C into what? IC bar. Yes, students, today we come across what's the position vector of in center. The position vector of in center is OI bar is equal to, yes, come on, That is A into OA bar plus B into OB bar plus C into what? OC bar by A plus B plus C. So, or else I can also write OI bar is equal to A into X bar plus B into Y bar, C into Z bar, that is C into Z bar plus A plus B plus C. This is one of the important result for the objective purpose that comes in the word addition of vectors. Remember, so therefore A into IA bar plus B into IB bar plus C into what? IC bar is equal to 0 vector or a 0. If you know this concept of this, then you can get this result and also this result. Yes, we have arrived at what? One important what result on in center is what? Come on, OI bar is equal to A into X bar plus B into Y, that is Y bar, C into Z bar by A plus B plus C, or that is A into IA bar plus B into IB bar plus C into what? IZ, that is IC bar is equal to what? 0. That is A into IA bar plus B into IB bar plus C into IC bar is equal to 0. In a triangle, I want to know that what is the orthocenter, what is circumcenter. So therefore, in a triangle ABC, the point of concurrence of altitudes of a triangle, the point of concurrence of altitudes of a triangle is known as orthocenter. But this is AD is a what? Altitude which is perpendicular to the opposite side, So therefore, now the point of concurrence of altitudes of a triangle is known as what? Orthocenter. And also, look at, and also, in case of right angle triangle, the point of intersection of perpendicular sides is a what? Orthocenter. Okay, now we come across about what's the definition of orthocenter. Now if I go to what? Circumcenter. What is circumcenter? In the circumcenter, that is A, B, C. You take D is a midpoint. You take what? Come on, F is a what? E is a midpoint. F is a midpoint. Therefore, now if I take the what? S is a what? Circumcenter. The point of concurrence of perpendicular bisectors. These are the altitudes. The perpendicular bisectors never passes through the opposite vertex. So therefore, this is D is a perpendicular, this is also perpendicular, this is also perpendicular. But it's a midpoint and perpendicular. But here it is only perpendicular. Altitudes never meets at midpoint, but only perpendicular bisectors meets at midpoint and they are perpendicular to each other. So therefore, the point of concurrence of perpendicular bisectors of the sides of a triangle is known as what? Circumcenter. In case of right angle triangle, say for example, if I go to the what? Right angle triangle, the angle in a semicircle is what? 90 degrees, correct? Angle in a semicircle is what? 90 degrees. So therefore, the side opposite to 90, will be the diameter. The side opposite to 90 will be the diameter. So therefore, the midpoint of the hypotenuse will be the what? Circumcenter. Circumcenter means if I draw a what? Circle. If I draw a circle, the circle is passing through what? 3 points. So therefore, now if I take D, this is nothing but a radius. This is nothing but a radius. This is also radius, correct? This is also radius. This is what? General triangle. This is a right angle triangle. In a right angle triangle, the point of intersection of perpendicular sides is the orthocenter, and the midpoint of the hypotenuse is what? Circumcenter. This is for right angle triangle. This is for any triangle except equilateral triangle. So therefore, now when this circumcenter is the point which is equidistant to the three sides. The circumcenter is the point which is equidistant to the what? Come on, equidistant to the what? 3 points A, B, C. Whereas incenter is equidistant to the 3 sides. So therefore, incenter is equidistant to the 3 sides. Circumcenter is equidistant to the 3 points, means 3 vertices. Hence, we take this as a radius. This is also radius. This is also radius. Here also, this is also radius. This is also radius. This is also radius. I told this is a circumcenter. In any triangle, the circumcenter is the point equidistant to the vertices of a triangle. So therefore, I can write this one as SA is equal to SB is equal to SC is equal to what? R. What is that? It's a radius. It's a radius. Yes. Today we come across about orthocenter. What is orthocenter? Orthocenter is the point of concurrence of altitudes of a triangle, is known as what? Orthocenter. In case of right angle triangle, the point of intersection of perpendicular sides is what? Orthocenter. Then I came to what? Circumcenter. What is circumcenter? Circumcenter is the point of concurrence of perpendicular bisectors of the sides of a triangle, is known as what? Circumcenter. And circumcenter is the point equidistant to the 3 vertices. In case of right angle triangle, midpoint of the hypotenuse is the what? Circumcenter. And the point of intersection of perpendicular sides is what? Orthocenter. Here also, circumcenter is the what? Because angle in a semicircle is 90 degrees. The circumcenter is the point. The side opposite to 90 will be the diameter, and the midpoint of the hypotenuse is circumcenter. And circumcenter is equidistant to the 3 points A, B, C. Hence, you can say that SC is equal to SB is equal to SC is equal to what? R. What is R? Radius of a circle.